There isn't always a condensation funnel if the boundary layer is too dry. But you'll still see debris spinning up, assuming there's some debris to spin up. So this, as I've been talking, this thing has just formed a tornado. You still see these little glowy bits coming in. That's rotation, and there is a story to be told about vorticity in this simulation for sure. But you know, this kind of simulation we've been doing. When I say we, the scientific community has been doing work in this area, three-dimensional cloud modeling, since the late 1970s. But this is kind of pushing it to a new limit, I think. Here again, we're looking at vorticity long before the storm forms a tornado. Here's the major updraft, the mesocyclone. I'm shading it by the updraft, so where you see like it going from gray to yellow to red, it means the air is getting sucked up, which is pretty obvious by looking at it, but it also helps to sort of quantify it a little bit. Now, as time goes on, you're going to see the tornado form right about here. Some of the lighting's a little bit funny, but you'll notice that there's no trigger, there's no magical switch, there's no signature that just shows up, and there's our tornado right now. This will run for quite a while. I'm trying to show essentially the basic structure of what's going on. Keep in mind that the entire storm is moving towards the northeast at about, say, 30 miles an hour. The way we model these storms is we subtract the storm motion out of the solution so that we can follow it along. There was a vortex that grew out of the ground almost, and then wrapped around the tornado, and then went up the tornado. I'll show you some of this much slower so you can see it better shortly. There's all sorts of fascinating things. Here's the rear flank of the storm. Here's one of those rear flank surges that occurs in the supercell. Now, the tornado's been on the ground for a half an hour by now. We still see activity from the rear flank. A lot of the activity you see from the rear flank, however, is air that's scooted around the bottom of the meso from the forward flank. A lot of time when you hear people saying RFD, RFD, RFD when they're chasing, I suspect they're actually in air that may have originated from the forward flank that is coming around the mesocyclone. And now the tornado is taking on a two-celled structure with a downdraft in its center. This has also been verified by chamber models and other models. So everything looks pretty darn good. I mean, there's some issues we have with rain centrifuging, and that we don't have it built into the model physics. In the real atmosphere, if you look at a tornado that has rain in its vicinity, you'll have a little hole in the center because the rain, due to its higher mass, gets centrifuged outwards through the air. That type of physics has to be put in the model. It turns out it's a kind of a complex problem. So our tornado has rain in it where it shouldn't be. That's a problem we're going to fix. But again, this thing is on the ground for an hour and a half or more. It's still churning along. There's just so much to be seen and studied in this data. It can be overwhelming at times. Notice how the rear flank sometimes kicks out these vortices, and they take several rotations around the tornado before they get sucked up. When you have anticyclonic or clockwise vortices interacting with the counterclockwise or cyclonic tornado, it does all sorts of weird things. Now this thing's dying. It's downdraft, just downdrafts falling down, sort of squashing the tornado. You'll see a lot of horizontal vortices, a lot of kinetic energy is being redistributed. It's not visible in this image, but the rain, it's now a rain-wrapped tornado. It's pretty much, you can still see evidence of the rotation here. It's still pretty strong, but it's in the process of getting wiped out as it gets completely encircled by rain. So this is basically an overview of the full simulation. And again, if you go to a lot of talks, you often don't get this much video. I've managed to make a lot of video. Here's the streamwise vorticity current that we've identified. This is along that forward flank again. Just watch the particles go. I mean, I can write a paper about this and describe it in words, but I can show this video and you can say, oh, it is moving helically, it is horizontally oriented, it's being tilted, it's being lifted, it's being stretched, it's being brought up. It's all in here. But what we have to do is tag these parcels and trace values of different physical quantities along their path. That's a very powerful technique in meteorology called Lagrangian parcel analysis, where you follow the air around and see the forces acting on it and then try to figure out what's going on. I'll run this one. Some of these will go faster, some will go slower. This is, again, showing the generation of the tornado genesis. We're looking west now, so here is the air streaming in from the north. This is that SVC thing that we've identified here, those vortices that you would see. This would be the ghost train in this case, if you're thinking in that term. The strongest inflow on the warm side is right along this boundary. A lot of chasers like to hang out in the rear flank of the storm, which is good to be safe, usually, because